Page 10 of Applications of Calculus. Number 1, when a manufacturer makes X items per day, the cost function is C of X equals 720 plus blah 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 dollars, and the price function is blah 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 per item. Find the production level that will maximize profits. So these business problems assume that you know a little bit about the terms cost and price, sales. Just to make it clear, cost is what the company pays to make it. So it's like how expensive it is to produce in the factory and that kind of thing. It's not how much it's sold for. How much it's sold for is sales or price. So price is what the customer pays. And so the difference between price and cost is profit. Okay, so profit equals price minus cost. Hopefully you never get an IB problem where you're assumed to know that. But maybe it's something you should write in your note card to memorize right before the exam. So they make X items, and the cost, let's see, it's not really clear here. Okay, so the cost is, I think, how much it is to make a certain number of items. So it's not like an individual cost for one item. It's like for all the items. Okay. Price function is per item. Notice that it doesn't say per item for cost. So in order to subtract the two from each other, price minus cost, you have to use the same number of products, right? So if price is per item and cost is for all the items together, then we do need to take the P function and multiply it times the number of items before we subtract the cost function. Otherwise, we're not comparing apples to apples, okay? So what we're going to do first is we're going to have a profit function, which is equal to the price function times X, the number of items, minus the cost function. So let's write that out. So the price function, remember, is 15 minus 0.002x, and then we're going to multiply that times x, and then we're going to subtract the cost function, which is 720 plus 4x plus 0.02x squared. And then we want to maximize this quantity. So of course we're going to take the derivative eventually, because in order to find the maximum point we need to find the derivative and set it equal to 0, right? So we're eventually going to do that. So first let's simplify this function. We're going to have, what do you call it? We're going to distribute the x to the 15 and the 0.002. So we'll have 15x minus 0.002x squared. We're going to distribute the negative sign to these three, so it's negative 720 minus 4x minus 0.02x squared. And then we're going to group like terms, so we'll group these two and we'll group these two. So it will be negative 0.022x squared plus 11x minus 720. And this is our profit. This is our profit function. So I'm going to call that, to not call it P, we already have a P, I'll call it F or R. It's my R function, profit. And in order to find out where the maximum point is, since this is the calculus unit, I'm going to take the derivative. And so it would be negative 0.022 times 2x to the first plus 11, remove the x, and negative 720 just disappears. I'm going to set that equal to 0. And then I'm going to simplify and solve by adding 0.044x to both sides. I end up with this. So x is equal to 11 divided by 0.044, which is equal to, use the calculator, 11 divided by 0.044. It's equal to 250. So 250 items is when the profit is maximized, and the production level means how many do you make. So X is the number of units, so it's 250 units. Number 3, another business problem. A manufacturer can produce X fittings per day. Fittings, what's a fitting? It's just some metal part. Where X is between 0 and 10,000. The production costs are 1,000 euros per day for the workers, 2 euros per day per fitting, 5,000 divided by X per day for running costs and maintenance. How many fittings should be produced daily to minimize the total production costs? I thought that this problem wasn't very clear as far as like which one of these costs are per fitting and which ones aren't. I also thought it was odd that like it was actually cheaper total to make more fittings than a smaller number of fittings. That doesn't really make any sense. Like, why would you be able to make more fittings for less money total? But anyway, that's the way they wrote this problem. So anyway, so like this, notice that this one says per fitting and the other ones don't. So these other two, you can assume that it's like the total cost no matter how many fittings you make. So when we make the cost function, we're going to make a cost function for the total number of fittings, okay, not per fitting. Although in a real problem, I think it would make more sense to do a per fitting cost. So the components are this €2 per day per fitting. We need to multiply that times X because we're going to do a per fitting or a total cost, not a per fitting cost. And the 1,000 and the 5,000 divided by X, those two components, they don't say per fitting, so we just use them as is. Okay. So how would we find the minimum point, because we're looking for a minimal cost? Well, we're going to go through the couple steps that we use calculus to do so. What we would do is we would first take the derivative of the cost function, and we would get 2x, the derivative is 2, 1,000, the derivative is 0, and 5,000 x to the negative 1. If we rewrote this, it would be 5,000 x to the negative 1, right? The derivative of that would be negative 1 times 5,000 x to the negative 2, right? So the derivative would be 2 minus 5,000 divided by x squared, and then we would set that equal to 0 because we want to know when the derivative is 0 to find where the minimum point is. And then if we simplify, or if we solve that, we would multiply both sides by x squared to get it out of the denominator. So we get 2x squared minus 5,000 equals 0. Then we have 2x squared equals 5,000, and then we have x squared equals 2,500, and then we have x squared equals the square root of 2,500, or x squared, or x, sorry, if we take the square root of both sides, it would be x equals plus or minus 50, right? Because 50 is the square root of 2,500, and of course, x has to be a positive number, so we reject the negative 50. It's basically x equals 50. Okay, so x equals 50 would be where the minimum point is. To make sure it's the minimum point, we could take the second derivative of this function just to confirm that it is the right concavity. If we took the second derivative of this function, it would be 4x, right? And the derivative of negative 5,000 is 0. So the second derivative is going to be 4x. And if we put a positive number in there, it's a positive concavity, which means that it is a minimum point. So 50 is a minimum point like we figured. So the number of fittings that should be produced per day to minimize the function should be 50. By the way, another way you could do this without calculus is to put the original C function in the calculator, graph it, and when you graph it, you can see there's a minimum point right here. We can find that, of course, by doing second calc minimum. Okay? Let's go on to number 5. Okay, another business problem. The cost of running a boat is v squared over 10 plus 22 pounds per hour, where velocity is the speed of the boat. Okay, so v is the speed of the boat, and that's like the input function to find out the cost of running the boat. And this is per hour. Find the speed which will minimize the total cost per kilometer. Okay, so basically we have a cost per hour, and we would like to multiply that times some kind of conversion factor and get cost per distance. So basically it looks like we need to multiply by hours divided by kilometers, right? Because then the hours would cancel out and would leave kilometers. Kilometers per hour, hey, we already have that. It's the velocity. So basically what we're doing is we're going to divide by the velocity. Look, if we divide by the velocity, then kilometers per hour is going to be upside down. It's going to be kilometers on the bottom, hours on top. So what we want to do is we want to take this original function, which is per hour, and we're going to divide by the velocity, or multiply by 1 over the velocity, and that is going to give us a cost function, which is per kilometer. Okay? That's what we have shown here. So let's just simplify this. We're going to distribute 1 over v to both. So we'll have v over 10, and we'll have 22 over v. And here is our new cost function, which is per kilometer. And I'll call it c. Okay, and then we want to find the speed, which minimizes the total cost per kilometer. So we're going to take the derivative of the c function. And that means the derivative of v over 10, which is going to be, this is the same thing as 1/10 v, right? So when you take the derivative of derivative of the velocity, the derivative of the cost function with respect to velocity, you would just leave 1/10, because 1/10 v, you would just remove the v, right? And the next one is, we could rewrite it as 22v to the negative 1, and when we take the derivative of that, it would be negative 1 times 22v to the negative 2, which is equal to 1/10 minus 22 over v squared. So this is the derivative function, and we set that equal to 0 to find out when the minimum point, where the minimum point would be, and then we start solving it with just some algebra. And let's multiply both sides by v squared. So we'll get v squared over 10 equals 22, and then we'll isolate the v squared. V squared equals 220, and then the v is equal to positive or negative square root of 220, but probably the velocity is going to be positive, so we'll just consider square root of 220, which is square root 220. It's about 14.8. So 14.8 kilometers per hour is the velocity, which will optimize the cost of running a boat. Number 9, last business problem for the day, or for this page. A manufacturer of electric kettles performs a cost control study. They discover that to produce X kettles per day, the cost per kettle C of X is given by this function, with a minimum production capacity of 10 kettles per day. Okay, so this function has a domain of greater than or equal to 10. How many kettles should be manufactured to keep the cost per kettle to a minimum? So this is a cost per kettle function. All we need to do now, they already have it all prepared for us. We don't even need to like modify it in any way. And then all we need to do is take the derivative so that we can find when it's equal to 0, and then we'll find the minimum. Okay, so what is the derivative of this function? It's going to be 4, derivative of natural log of x is 1 over x. The derivative of 30 minus x divided by 10 squared, first we're going to do the derivative of the outside function, which is the squared, and then we leave the inside the same, chain rule, right? Reduce the exponent by 1. Then we're going to multiply by the derivative of the inside. Derivative of the inside looks like we have 30 over 10 minus x over 10. So the derivative of 30 over 10 is 0. The derivative of x over 10 is negative 1/10. So simplifying, we have 4 over x plus, let's see, negative 0.2. I combine 2 and negative 1/10. And then on the inside, I have 30 minus x divided by 10. If I simplified this, I would have 4 over x, and then I would have negative 0.02, and then 30 minus x in parentheses here. And so this is my derivative function, and I'm going to set it equal to 0. So I'll have 4 over x minus 0.02, 30 minus x equals 0. And then I'm going to multiply both sides by x, so I'll have 4 minus 0.02, 30 minus x, and then equals 0. Oh, there's a x here too, right? I multiplied both sides by x. So I multiply this side by x, I multiply this by x, 0 stays 0. The left side becomes 4 minus 0.02, parentheses 30 minus x times x. We're going to distribute the x to 30 and to minus x. We'll get 4 minus 0.02, 30x minus x squared equals 0. Then we distribute the 0.02 to both, and we'll get 4 minus 0.0 times 30 would be 6.6, negative 0.6x. Okay, and then distributing negative 0.02 to negative x squared gives us positive 0.02. X squared equals 0. So now we have an a value that's 0.02, we have a b value that's negative 0.6, and we have a c value that's 4, and we just need to find out what x values make that true. We can do that with polysmlt, so we go into apps, polysmlt, and then we type in our a, b, and c values, polyroot finder. Next, so we're going to put in 0.02 for a, we're going to put in negative 0.6 for b, and then we're going to put in 4 for c, and solve. And our answers are 20 or 10. So we know, okay, so we don't know which one of these are minimums and which ones are maximums. How do we figure it out which one's a minimum, which one's a maximum? We could take the second derivative, and we'll get negative 0.6 plus 0.02 times 2x, which would be negative 0.6 plus 0.04x. And basically, any x value that is 10 or above, let's see, is going to make that, yeah, so like actually, okay, so if we do a sign diagram for the second derivative, we'll see that the 0 for this occurs at, let's see, 0.04x equals 0.6, x equals 0.6 divided by 0.04. It's going to be like 15 or something. .6 divided by 0.04. 15. Okay, so at 15, the concavity changes. On the right side of 15, if I put a big positive number into this expression here, then I would just get a big positive number out. If I put 0 in here, I would get negative out. So basically it looks like this. Concavity switches at x equals 15. Here it is concave down. Here it is concave up. So in the case of 20, it is a minimum point. And in the case of 10, it is a maximum point. So we want the minimum point, so we'd want 20. So 20 is our solution for how many kettles should be manufactured to keep the cost per kettle to a minimum. Okay, so that's it for this page.